Right, so welcome to the session on Bayesian networks. So this is from week 5, and today we're basically going to be going through Bayesian networks in a way that doesn't make it too complicated, in like what you actually need to know for the exam. And yeah, because a lot of the content from week 5 Bayesian networks is non-assessed and not from Atta's recent lecture, but because the slides in fact say it's non-examined material. Some things like approximate inferences, that's not assessed, so we won't be going into that. We'll be going into the stuff that will definitely come in the exam, like Bayesian networks in general, exact inferences, and all the different types of connections, probabilistic relationships, and so on. So without further ado, let's get started. So from the top, a probabilistic graphical model, which is what a Bayesian network is basically a graph where nodes represent random variables and directed edges, which are called links or arcs. We know this stuff from DSA, represent conditional dependence between these variables. So when you have one node pointing to another node, it means that the node being pointed to has a probability that's dependent on the node that's pointing to it. So it is conditionally dependent. That's what we mean when we say that. So Bayesian networks use the direction of edges to represent the cause-effect relationship and Bayes' theorem for probabilistic relationships. So as I just said, the cause is the one that is doing the pointing, and the effect is happening to the one that's getting pointed to. Therefore, they are conditionally dependent. And the other key rule to note from the get-go in Bayesian networks is that loops of any kind are not allowed, because if you imagine the reason why, you don't really need to know why, but you'd have a cyclical pattern of things depending on each other, where you would not be able to find like a source of an independent event. So you can't have everything depending on everything. So loops are not allowed. Going through quickly before we jump right in, why would you need a Bayesian network? What are its advantages? What are its drawbacks? So obviously, a graphical representation is always welcome. We like to see things visually. It provides a very visual representation of the probability distributions we're working with, and also one of the best I've seen where you have lots and lots of conditional variables that, affect each other. Yeah, this kind of stuff. This stuff was in the slides, but it's basically glazing Bayesian networks more from just saying like it's good for viewing, essentially. There's the fact that it's a generative approach. So we did look last time in my naive Bayes session at generative and discriminative classifiers. So similar to that, Bayesian networks takes a generative approach. So it's generates new data, which is similar to the existing data. And it does this because it can look at a label and then kind of generate the data, as opposed to doing it the other way around, which may seem more conventional, where you see the data and try to generate a label. And as some of you will remember, naive Bayes, which we'll look at now, was a generative classifier. So you can use Bayesian networks to model naive Bayes. If we look at this, for example, this is an example of a naive Bayes classifier modeled as a Bayesian network. Y is the label, the thing that normally you'd be trying to predict, and the X is the feature vector. So you've got a bunch of features that influence a label, except no. In this case, it's all reversed. You'll actually see that Y is pointing to the feature vectors. The list of features. So that means Y is influencing the features, not features influencing Y. And that's what's important to note here. So where naive Bayes is a generative classifier, which we know, right? What that means, if you go back to the definition of generative, is that we know the probability of the data, we know the probability of the features given the label, and we use Bayes' rule to reverse that. So we get the probability of the label given the data, which is what's useful to us. So we know the probability of the feature given the label, but we want to get the probability of the label given the features, and we use Bayes' rule to get that. I hope that's clear. And then, that's why it explains the direction of these arrows. Other thing to notice, because just going back to the naive Bayes assumption, there are no arrows between the features. And this is due to the naive Bayes assumption, which many of you will remember, is that it assumes all features are independent of each other and there's no relation, which is one of the limitations of naive Bayes. And that's why there's no further arrows between them. So that's naive Bayes modeled as a Bayesian network. We could be asked something about that. It's not been ruled out. But anyway, let's move on. So I think in understanding Bayesian networks, the Markov condition and the Markov blanket, especially understanding what assumptions and things we take for granted in making a Bayesian network, is so crucial to understand before you can actually grasp why things occur the way they do in more complex Bayesian network relationships. So, what does the Markov condition state? It states that each random variable x is conditionally independent of its non-descendants, given its parents. And this means that the parent cannot be conditionally dependent on its child, and all Bayesian networks have this as the underlying assumption. This simplifies computation, but obviously can introduce inaccuracy because it's not a perfect representation of reality. So, here we can see an example. I'll just tell you in plain English what all of this means. This is a Markov blanket, but in plain English, all this means is basically we assume that if you know the direct causes, so if you know the parents of a variable, then knowing anything else upstream, sideways, down in the graph won't help you predict it better. Knowing the parents is enough, essentially. The Markov blanket takes that further and says that so the Markov blanket of a node is basically the node's parents plus the children plus the children's parents. And what that means is you can see for x here, this node x, we are showing its Markov blanket on this image here. You've got its parents, you've got its children, and then you've got the parents of those children as well. And it's said that if you take the Markov condition as assumed, then you can infer all information you could possibly want about x purely based on this segment of the graph here. And from the Markov assumptions, we get this crucial formula which dictates to us how we will treat a lot of conditional dependence later on. We have a question from Hux. Let's see. What exactly do we mean by conditionally independent? Does it mean not conditionally dependent? Probability of A. Yeah. So conditionally independent is a tricky one. I can see why that seems like a juxtaposition in so many ways. So how that works is it's independent given a condition. And we'll look at that later. So I'll just to satisfy the question for now. If you have, let's say, a common cause. So A is a cause of B and it's also a cause of C. We say B and C are conditionally independent because given the condition of A, then you know B and C are independent of each other. But we will touch on that further as we go along. So let's move on to the steps needed for Bayesian networks. Basically, 3-step protocol, similar to most models that we know. Inference, you run tests, observe the data. Obviously, this is where you get the data you need. Train the model will learn parameters. And then you structure determination. So this is where you identify what is dependent on what, and then you test. Oh, and it's important to note here that the test for independence is the probability of A and B is just the probability of A multiplied by the probability of B. You did this at GCSE, A-level, whatever, like it's the same thing from there. Another question in the chat, let's see. Right, so yes, exactly. So yeah, that's correct. Okay, cool. So, types of probabilistic relationships. Here, we can see the 4 types of probabilistic relationships that we're required to know for the exam for Bayesian networks. Part A, direct cause, the simplest of them all, but Atta Kanban said was not going to come up, but you need it to understand the rest, to be fair. B is dependent on A only, so the probability of A and B is equal to the probability of A multiplied by the probability of B given A. And this is nothing new. This is, if you think back to... Oh yeah, my bad. Okay, wait, they've got another question in the chat. No IDTS. Probability of A, or if probability of B are conditionally independent, surely. What? I don't think so. Oh, right. Probability of A given B is equal to the probability of A if and only if A and B are conditionally independent, surely. The probability of A given B, yeah, so the probability of A given B should be... Your question there, what do you mean by are conditionally independent? To be conditionally independent, you need to have a third variable involved. You can't have A and B and have conditional independence. That would just be either dependent or independent, since that's direct cause. That's not any of the other types where there's a third one involved. Shay. But they're still conditionally independent from each other. They're just independent. Like A and B in that case would be independent. Yeah, exactly. So Fred said it perfectly there. So A and B are independent given C. That's what I'm trying to say. When you, in your question, Shay, when you have A and B, that's just, you're testing for independence. Conditional independence requires there to be another variable present in order for a condition to be satisfied for the other two to be considered independent or not. Now, the other two, we can't call them independent because they are still based on a parent, a single common cause, which is why it's conditionally independent. Whereas when it's two, you can have independence and you can have dependence just as normal. Cool. Let's move on. So, you can calculate the probability of... so as I said, this was just the stuff we learned at GCSE, A-level, whatever. Then you can calculate the marginal probability of B by doing the probability of B equals 1. So I'm assuming here that these are binary random variables. And we looked at in the naive Bayes session what marginal probability was. And essentially, this is the denominator for Bayes' rule, which we ignore in naive Bayes, actually. But yeah, that's what marginal probability represents. And you can use this with Bayes' rule to infer the reverse probability. So if you have the probability of B given A, then you can get A given B by calculating the marginal probability using this formula here. Essentially, assuming B is dependent on A, so you just multiply the prior probability, so you multiply the probability of A occurring, so the probability of the causa occurring, multiplied by the probability of the effect occurring given we know what the cause is. And then you do that across all the different causes. So here, since it's binary, the only two causes can be 0 and 1. So we'd, work through this formula once with A being 0, and then we'd work through again with A being 1 and see what the probabilities are for both, for B. And then we'd add them up and that would give us our marginal probability. That comes useful later on, but we have covered that in the past, I believe, in some other sessions. Indirect cause is the second type of relationship here. So C is dependent on B, which is dependent on A. So the probability of A and B and C is equal to the probability of A multiplied by the probability of B given A, because you've got A by itself independent. Now B given A, so that's there. And then the probability of C given B. Now, I had a question yesterday where we were asking, why is it C given B and not C given A and B? Because surely C, by being dependent on B, is also dependent on A. Well, truth is, it is actually dependent on A and B. This is more accurate. But, as we said, when we do Bayesian networks, we take into account this Markov assumption. This Markov condition is held to be true. So, because of the that conditional independence assumption, where we only rely on its parents to give us information about the node, in the Bayesian network, we don't need to then worry about its grandparents, ancestors, family tree, doesn't matter, right? We just look at the parents. Now, yes, as I said, that does pose limitations and inaccuracies, but it makes computation much more simple. Next, we have the common cause, C. So the common cause is called also conditional independence. It's what all the racket's been about so far in the chat. Let's see what the questions are. So P probability of C given AB is equal to the probability of C, and it's also equal to the probability of C given A. So the probability of C given AB is equal to the probability of C given B in a Bayesian network because of the Markov assumption. In reality, it's not, but for the purposes of the exam, yes, it is, okay? And then it's also equal to the probability of C given A for indirect cause. What? Oh, right, the top two, C given A. No. C given A is, you wouldn't write C given A because C is not a parent. Sorry, A is not a parent of C. So it has no bearing on the thing. But yes, in reality, yes, you can infer C from A, but for the purposes of the exam and due to the Markov assumption, you were using this formula here, which you only consider its parents. Does that make sense? Okay, yeah. If A was a parent of C, then would it have to be written as the probability of CAB or just C given B? So if A was a parent of C as well, so if there was an arrow from A to C essentially as well. Well, firstly, right, that would not be allowed because what does that create? We learned at the start, we're not allowed loops in Bayesian networks. So that is actually an invalid Bayesian network to begin with. But even if that was the case, it does. You can't have you can't have this kind of stuff in a Bayesian network because that would create a loop. What is the diagram on the slide yesterday? So you're talking about the slide. I'll bring back the slide real quick. Okay, let me just check. 1 second. So the slide yesterday, by the slide yesterday, are you referring to essentially, wait, let me show you this. Wait. So the slide yesterday, right? This image here, and I've just pasted this in from the slide right now. So it says the following are not allowed, and what you've suggested here, where you have C pointing to both and A pointing to B as well, is in fact one of the ones that do count as a looping graph and are therefore prohibited by Bayesian networks. So you won't be allowed that. The question we were asking yesterday in labs, Shay, was in fact a completely wrong question because that wouldn't have been allowed anyway. Like we were asking the question wrong, don't we? We should have understood the thing before asking the question. But yeah, anyway. So yeah, that's why you only consider its parents, and you can't have loops as well. So you won't get a question essentially where it points to two things like that because it's not allowed. Okay, cool. So that takes care of the second kind of probabilistic relationship in Bayesian networks. Let's look at part C, common cause, the third kind. So in common cause, this is called conditional independence. It's been what the fuss in the chat was about at the start, to be fair. And what it states is that two variables are independent given a third random variable. And as Hux mentioned as well, A and B are independent given C. And Fred also mentioned this, to be fair. If probability of A and B, if and only if, sorry, that should be if and only if. If and only if the probability of A and B given C is equal to the probability of A given C multiplied by the probability of B given C. So as you can see, this part, probability of A given C multiplied by the probability of B given C, is actually similar to what we do for a test of independence. But all we do is each time we have to add in given C, since now they are not independent, but they are conditionally independent. I hope that makes sense now. And I don't see any more questions about that, so that's good. And finally, part D, you're least likely to get this in terms of like the questions I've looked at, but it's also one that could come up. Common effect. So this is basically the opposite of above, and it means that two parents are independent given a child, rather than two children are independent given a parent. So how that would look here is that you have C, right? So given C, then A and B are independent, but so they're actually conditionally independent given C. So it's similar, but like the opposite way around. And yeah, essentially that's what we need to know about the four kinds of relationship, the probabilistic relationships you could be given in any Bayesian network. Does everything make sense so far? Is there anything that I've covered that, is anyone still unsure about, or is it all clear? So in all of these, we're computing the joint probability of all variables being on. Yes. Yeah. So if you are, I'm assuming what you're asking here is, are we kind of calculating the probability, assuming that these are all binomial random variables, meaning they can take a value of 0 and 1. And yes. Sorry, not binomial, binary. Yes, and the answer is yes to that. Hux is typing. Let's get this question in, and then we'll move on. Damn, the suspense is real. I get nervous when Hux is typing because I don't know what question I could be asked. Okay, let's see. Okay, here we go. So, there are four kinds of shapes in the network. Do they imply the probability relationships, or do we go, hey, this is on parent with two kids. This is on parent with, this is probably one parent. One parent with two kids. Let's check if the probability relationship is true by calculating probability of A given C multiplied by the probability of B given C. I mean, so the probability of the test of conditional independence, where you have A and B being conditionally independent based on C, that is the test for it. The question, in the network, do they imply the probability relationships? Yeah. So what these? Oh, right. So these do imply what affects what and the probability relationships. They're called the probabilistic relationships. That's their official names. Does that make sense? They tell us like the what affects what causes what, and so on. Yeah, so the cause effect relationships. Right. I feel like we can move on to a worked example if there are no more questions. I'll let you type out your question, Hux, and I will read it once I've just started explaining this worked example. So this is the worked example, the famous wet grass worked example. So the premise of this is that there is a variable, cloudy, right? So these are all going to be taken today as binary variables, and to be fair, in the exam as well, I doubt they'd give you any like other kind. So it's either 0 or 1. So 0 means it's not cloudy, 1 meaning it is cloudy. So we have this probability given. Then also, there are two things that can make the grass wet. Either it can rain, or the sprinkler can turn on and make the grass wet. So these tables here represent the probability of, for example, the sprinkler being on or not, and here for it to rain or not. And as you can see, these two, as we've discussed above, are conditionally independent. Because if we know C, then we know these two. Then beneath that, we have the common effect relationship, because we would have wet grass over here. Now, the question would be, provided we know that it's cloudy, what is the probability of the grass being wet? Does anyone want like a second or two to have a go at the question, or should I just show the answer? In the meantime, I will read and answer Huxka's question. So, makes sense. I just want to double check I get it. Right, so when I see two nodes with the same parent, I know they are conditionally independent given the parent. So, I can use the probability of A and B given C is equal to the probability of A given C, probability of B given C, to calculate stuff. Yes, exactly. So if you know they're conditionally independent, then you can definitely at all times use that formula to calculate stuff, because it will always be valid if and only if though the two variables are conditionally independent. Calm. Okay, cool. So this was the worked example I had on the screen, and yeah, if I scroll down, this is the answer. So what we've gone through here is we've gone through, as you can see, the probability of the grass not being wet and the probability of the grass being wet. So these are two classes essentially, and the two variables it depends on is S and R, sprinkler and rain. Notice C is nowhere to be seen because we're using a Bayesian network, and the assumption, Markov assumption, states that only the parents are to be considered. And therefore, we don't need to worry about C anymore. But we needed to worry about it when we needed to do rain and sprinkler. So in essence, if you were just given C and you had to fill in stuff here as well, you would need to worry about C. But because we've been given those, we don't. And here, what you would do is to work out the probability of wet grass given that it's cloudy. You would just simply work out the marginal probability from the data you have over here by multiplying so multiplying these probabilities by the probabilities of the marginal probabilities of these two, and from that you would get a normalized value, and then you'd sum these values up and get the final marginal probability. But this session is not on marginal probability, so I won't go too deep into that. Okay, so that is actually the first half of Bayesian networks covered. Not half, actually, that's more than half. A lot of it's been covered. There's just a little teeny bit left to do. So, inference. So, learning and inference from Bayesian networks. So there's going to be I'm just going to set up all the premises now before we dive into it. So there are two kinds of questions that inferences will help you answer in the exam. It can either help you answer a diagnosis question or a prediction question. The diagnosis question is when you are calculating the probability of a cause given the effect. So when you're calculating maybe the probability of a parent given the child. In a real life scenario, diagnosis, as you can tell, probably like medical conditions, if you have a certain effect, e.g. a symptom, right, what it could be the cause, then you would see what is the most likely cause. Prediction works the other way around, so you're trying to see how probable an effect is given that you know a cause. So, you know, yeah, it's pretty obvious. Like you can see that it's getting cloudy. So what's the probability of your grass getting wet, for example? Cool. Then there are three categories of variables itself within Bayesian networks. So anytime we have a variable, we can put it into one of these three categories, and it's important we know which is which later on. So we have evidence variables. These are what we know. Then query variables. These are what we want to know but don't know yet. And then we got the non-evidence variables. These are just a nuisance that neither known nor wanted, but you just got to deal with them. So yeah. And together, when you union all of them, you form a Bayesian network. So there are three main kinds of inference. So we had the two kinds of questions that it will answer, the three kinds of variables, and the three main kinds of inference. There are more, such as MLE inference, but the slides did not explicitly mention that, so I don't think we need to know it. So first type is unconditional inference, and this is like asking, what's the probability of something happening without knowing anything else? That's the first kind of inference. Then you have conditional inference. This is slightly more knowledgeable, right? This one says, given that I know something, what's the chance of something else happening? So for example, given I know that it's cloudy today, what's the chance of my grass being wet? Whereas the first one would have been, what's the chance of my grass being wet, period. Just like without knowing if it's cloudy or not. So as you can see, you start to develop a better picture of more accurate information the further you go. And then finally, you have map inference, so maximum a posteriori inference. And this asks, given what I know, what is the most likely explanation or best guess? And this is the formula for it. We will dive into this formula now because I can see it looks kind of daunting. But essentially, it's MAP, right? So you're trying to work out the probability of some data given the evidence. So these are the evidence variables, remember? So we know these. And you just do that by taking the maximum value of x from the probabilities you've calculated for all the values of x. Moving now, how can we use these three things, these three categories that we've learned? How do we use them? So exact inference. So there's two kinds actually. So there's exact inference and approximate inference. Approximate inference was in the slides, but it's like marked off as non-examinable material. So I'm not going to go through it today. But exact inference is marked as examinable. So this computes the posterior probability distribution. And we have a formula here. So this formula states that probability of x given e being the evidence variables, is equal to the probability of x and e over the probability of e. And this is then attributed to the formula alpha multiplied by the probability of x e equals the alpha multiplied by the summation of the probabilities of x, e, and y for all the different non-evidence variables, where alpha is 1 over the probability of the evidence variables. Now, you might be looking at me like, what the hell did you just say? Well, we're going to explain the formula. And I think once you know the formula, you'll understand exact inference and exactly its pros and cons. So the first part, right, this is conditional probability from A level and GCSE, to be fair. And all it states is that A given B is the same as the probability of A and B over the probability of B, where so B is the domain which you're comparing. So B is the entire population you're looking at because it's a condition you're holding to be true. And then you're seeing in that population of just B's, who is A as well, kind of with people, I guess. Then, because now it gets complicated a bit more from there. So because computing the probability of the evidence variables is often hard, especially on really large networks where you have very, very deep and like multiple layers, we use a shortcut. So instead of dividing by the probability of E as it's stated here in the formula, we compute the unnormalized value, which is the probability of X and E, and multiply by a constant, which is alpha. This is just 1 over the probability of E. It's literally the reciprocal of the probability of E, and which is why we can multiply it by it instead of having to divide by it. And essentially that's what we've written here. That's the next stage of the formula. Now, there's another twist to this. You can't directly compute the probability of X and E, unless you also consider all the other hidden variables in the network. So do you remember the Y's I was talking about? The things that no one really wants and we don't know either, but you have to deal with them anyway. So that's where they step in now. So the probability of X given the evidence variables is equal to alpha, which is 1 over the probability of evidence. And we sum that with all the different non-evidence variables, working out the probability of X, E, and Y. Just each time we swap out the value of Y for the next value of Y, and we just sum all of them together. So we have kind of the computation of the probability of X, E with every single Y value that is there. We're going to combine all XE with all the different Y values and then sum it up. And what this is called is, finally, we get to marginalization, which is what we need to know. Marginalization. So, marginalization is summing over all the values of the hidden variables to get the probability of what you care about. We love a good bit of summing over all the values of hidden variables to get the probability we care about. Then basically this is known as inference by enumeration, and the steps that we've taken essentially, if you look at this from a non-formulatic kind of view, is list all the variables. Nah, Hugs, what do you mean? So list all the variables in the network. Then step 2, we fix the values of the evidence variables. So in our cloudy and wet grass example, we're going to fix, let's say, cloudy as being true. We're going to take that as we know that cloudy is true. Then part 3, for each possible value of the query variable, e.g. like rain, which is one of the dependents of cloudy, it can either be true or false. We're going to sum over all the possible values, which is what we're doing here, and sum over all the possible values of every other unobserved variable, which is this summation here. And you're going to multiply them together and then sum them up. And then at the end, you multiply it by alpha, which is 1 over the probability of E, to normalize the results, just so they all add up to 1. You can almost like remove the probability of E from the entire thing till the end, because it's the same for all the classes, so it doesn't matter. It's just there for normalization at the end. And finally, I'm going to end with a limitation of exact inference. So what is the problem with this inference by enumeration? So there are it's really powerful at getting more accurate and more realistic results, but it comes at a cost. So the problem with being this specific is the number of terms you have to sum over grows exponentially with the number of hidden variables. So if you have n hidden variables where each has m possible values, then the total work you need to do is proportional to O of n times m to the n. So it's exponential complexity, essentially. So this is quite often why we stick to simpler things and use Markov assumption and so on. We get still a decent decent accuracy. Okay, there we go. But we don't risk over a very high complexity. But if you're working with smaller kind of data sets, this is very much still plausible. And that's the complexity of inference by enumeration. And that is the end of Bayesian networks and everything you need to know about them. Does anyone have any questions regarding the second part after I did a question session on the first part, so about the inference stuff? This stuff is generally a bit more complicated, so I'll try my best to answer some questions. I will end the recording here and we'll call it a day. I think there's another session at 4 p.m. actually, so not calling it a day, but yeah, essentially that's it for Bayesian networks. Thank you for joining, and I'll see you for well, someone else will be teaching it, but crypto at 4 p.m. Come. Bye, guys.